Assalamu alaikum warahmatullahi wabarakatuh, and welcome everyone. This is the lecture of advanced water and wastewater treatment. We are talking today about the topic of carbon adsorption. I am Dr. Muhammad Darwish, and let's start the class. So, what is adsorption firstly? So, as a definition, the process of accumulation of the substance at the interface between two phases, which, for example, liquid onto solid, okay, or gas onto liquid, or gas onto solid. So this is a natural process by which the molecules of a dissolved substance, which we call the adsorbate, okay, it will be collected on and adhere to the surface of a solid, which we call it the adsorbent. So we have adsorbate and we have adsorbent. So the adsorbate will be adhered to the adsorbent. The adsorbate will be adhered to the adsorbent. So this is the process of adsorption. So the adsorbent is the solid material onto which the substance will accumulate, while the adsorbate is the dissolved substance, the targeted pollutant, for example, that we are going to remove from the liquid. Okay, now basically we have two types of adsorption. We have the monolayer adsorption, okay, and we have the multi-layer adsorption. Now the main difference between the monolayer and the multi-layer is that, for example, this is the adsorption media, or this is the solid adsorbent, okay, and this is the adsorbate. So in the monolayer adsorption, it is only one layer of adsorbate is going to be attached to the solid, okay. So this is called monolayer because only one layer is attached, so there is no other layers will be contacted with the adsorbent. While in the multi-layer adsorption, it is that multi-layers or more than one layer is attached to the adsorbent. So here is the force which attach or adhere the solids, the adsorbate, is different than the forces in the monolayer. So the forces in the monolayer is depending on chemical forces only, while in multi-layer there is chemical and physical forces. Okay, so that's why we call it here is the physosorption. Okay, but in the monolayer is always called as a chemosorption case. Okay, so this is the main difference between the monolayer and the multi-layer adsorption. Right, and always in the adsorption process there is two opposite adsorption, two opposite processes happens or occur at the same time. We have the adsorption process, which is the adhesion or the association of the solids with the, association of the adsorbate with the adsorbent, while there is on the opposite side there is a desorption, which is the dissociation of the adsorbate from the adsorbent. Okay, both of them happen together, but what happens actually when we remove the chemical material, or we remove the pollutant from the water or wastewater using chemical adsorption, using the adsorption process in general, is that the adsorption rate is much higher than the desorption rate. So that's why we don't notice, or we can't notice the desorption, but it exists. Now this is a figure, shows the activated carbon, the material that we are going to apply or going to have some details on, that is going to be used as an adsorbent. Okay, so this is a magnified photo or a schematic photo for a one pellet of the adsorption of the adsorbent Okay, in the adsorbent we have different sizes of pore openings or pore sites. We have the macropores, we have mesopores, micropores. Okay, and the solids or the pollutants will be adsorbed to the pellets according to its size. So the smaller one will be adsorbed in the micro and the mesopores, while the larger pollutant will be adsorbed to the macropores. Okay, so each of them will fill the suitable size. And here is a bigger one that shows the adsorbate and how it is attached to the inside surface of the adsorbent. So the adsorption will happen on different sites. Some sites on the outer surface and some sites on the or inside the inner surface or the inner side of the adsorbent. And this is another photo. It shows how the carbon matrix have the mesopores and micro and macropores, and how the large and small organic molecules, they will enter and be adsorbed and captured in one small carbon matrix of granular activated carbon. So what is the applications, or what are the applications of the adsorption process in water and wastewater treatment? First of all, we use it to remove the dissolved odorous compound or trace organic materials in water treatment. And this organic material, we know that it causes odors in water. So normally we use carbon filters to remove the odor from water. Okay. Another application is to remove the chlorination byproducts, because we know that after chlorination there are some byproducts, for example the trihalomethanes, THM, and this one cannot be removed, or it's difficult to be removed by conventional means, and it's also harmful to humans, so it has to be removed. So one of the methods that can remove this byproduct is the carbon adsorption. And also one of the main applications to remove the dissolved organics that are refractory or inert material, which cannot be removed using conventional biological treatment. Okay, this is mostly in wastewater treatment. And also we can remove heavy metals from industrial wastewaters using some kinds of activated carbons that has the ability to adsorb or high capacity to adsorb heavy metals from industrial wastewater. So the most commonly used adsorbent nowadays is the activated carbon, actually, and this is made from any carbonaceous material, for example wood, coal, coconut shell, or many other activated carbon or carbon materials. Okay, of course the raw materials they have some adsorption capacity, but what we do is we enhance the capacity of adsorption by a process called activation. So what is the process of activating the carbon? So how is activated carbon prepared actually? So we have two basic steps. The first step is called the carbonation, and the second step is the activation. So what happened in the carbonation is that the material, or the raw material, is heated to more than or to around 700 degrees Celsius, and at that degree the charcoal or the char is produced. Okay, and of course heating should be applied in the absence of air. This is to prevent the destruction of the carbonaceous material. Okay, so it is applied, or the heating or the combustion, okay, and this is we call the carbonation. It will convert the raw material to charcoal. Okay, and then comes the process of activation. Activation process have different methods actually, but the most common one is to pass the mildly oxidizing gases, for example CO2 or steam, at temperature from 315 to 925 degrees. And this gas or oxidizing gas, when it is passed through the active or the char, it will form the pores and cracks. These pores and cracks is the enhancement of the char. These pores and cracks are the sites or the places, the locations that the pollutants will be captured in. So basically we have two types of activated carbon. We have the granular and we have the powdered. Okay, here are some differences between granular activated carbon and powdered activated carbon, but basically there is no difference in surface area per gram. For example, 1 gram of powdered have the same surface area of 1 gram of granular. Okay, but the diameter of the particles is different, of course. This is the diameter is from 0.4 to 2.36 millimeter, while for the powdered activated carbon it is less than 0.025 millimeter. Okay, so the smaller diameters means faster equilibrium. It will cause faster equilibrium. Okay, equilibrium means exhaustion, means the exhaustion of the capacity, means using the capacity of the activated carbon. Okay, these are some shapes, some types of the activated carbon. You see there is pellets here, you see the powder, is irregular shape, and so on. And this table shows a comparison between the GAC and a PAC, the granular and the powdered. Okay, you can see, for example, the surface area is almost the same. There's no such big difference. The bulk density is somehow there is some difference, but the effective size, I mean the particle size range, is also different. And you can see also the other difference. You can compare between GAC and PAC. Okay, now briefly, the mechanism of adsorption is that the adsorbates are held on the surface of the adsorbent by chemical forces. Okay, so the adsorbate is attached to the adsorbent by chemical forces, not physical forces. Okay, such as hydrogen bonds or maybe interaction and by van der Waals forces. So it is all chemical forces. But between particles themselves in the multi-layer, it will be a physical forces. Okay, so this is the main mechanism, and we will not go into details in the mechanisms. We just have a brief idea about it. So the molecules will continue to accumulate at the surface until the rate of adsorption equals the rate of desorption. As we said before, there is a rate of adsorption and there is a rate of desorption, always there, but we don't notice the rate of desorption at the first moment because it is very low compared to the rate of adsorption. But at equilibrium, at the equilibrium point, the rate of adsorption will equal the rate of desorption. Okay, so there will be no further accumulation will occur, and therefore there will be no more or no further treatment of the water. Okay, so this is the main or the basic idea of equilibrium. This is from one side of activated carbon water treatment site, and it shows how the water flow from the bottom to the top. Okay, so this is only for site installation. And in treatment plants, normally the GAC or granular activated carbon is applied for the secondary treatment effluent. You can see we have the preliminary treatment, the primary settling, biological treatment. This is a wastewater treatment actually. Okay, Here we have the chemical coagulation and sedimentation, then we have filtration, and then we have carbon adsorption. Okay, carbon adsorption process. And when the carbon is exhausted, of course, there is carbon regeneration, similar to the resins or the ion exchange resins regeneration, and then goes to the disinfection. Okay, and in other way, or in the treatment of water treatment, okay, of water, river water, we have the preliminary, primary settling, biological treatment. We have carbon adsorption or carbon regeneration, and disinfection. In this process, we don't have chemical coagulation and sedimentation, so directly we have a carbon adsorption and carbon regeneration, okay, and then disinfection. So the difference between path 1 and path 2 is there is no chemical coagulation and filtration. Why? It depends on the characteristic of water or wastewater that is going to be treated. Okay, now why we apply biological treatment and filtration prior to carbon treatment? As we saw before, we apply biological treatment and filtration before we apply carbon treatment. Why is that? This is for several reasons actually. The first one is, when we reduce the organic loads, we can have, or we can obtain, higher quality of effluent, and of course shorter contact time between the wastewater and the carbon. Okay, that means the treatment efficiency will be higher, and also the treatment process will be faster. Okay, and the second thing, we reduce the suspended solids by filtration. Okay, and we reduce also the colloids loads. This will minimize the plugging and the loss of the adsorption capacity of the activated carbon. So we will have longer working time, or longer active time of the activated carbon. Okay, and the third reason is that when we minimize or reduce the biological growth and the H2S production, okay, this will be minimized due to the less food supply to microorganisms, and consequently the process will be more efficient. So that's why we apply biological treatment and also filtration before we apply the carbon treatment. Now there are some limitations of activated carbon, of course. So first one, it is not efficient for high concentrations. Why? Because there will be fast consumption of carbon. Okay, the consumption of activated carbon will be very fast because the pollutants are very high concentration, and therefore we need very fast regeneration, and the process will be more costly. And the second limitation is that it's not very good at removing chemicals that are not attracted to carbon. Some chemicals are not adsorptive. Okay, they cannot be, or they are not so efficient to be removed by carbon adsorption, such as sodium, nitrates, some kind of heavy metals, and fluoride. Those chemicals or those materials, normally they are low adsorption, they have low adsorptive ability, so it cannot be removed highly efficiently, such as the other materials. Okay, and also activated carbon is not so efficient if the water does not stay in contact long enough with the carbon media. So we have to maintain a long contact time. Okay, we don't call it hydraulic retention time, we call it a contact time. So if the contact time is not very long, the treatment won't be so efficient. So that's also a limitation. We have to provide longer contact time. And finally, it's not effective against some pathogenic, like viruses or some kinds of bacteria also. In fact, it can be a site or a harbor for bacteria and microorganism growth, which will lead to side effects and more bacterial growth, which means that more pollution to the water. So the carbon filters, sometimes they are considered harmful and they increase the bacterial growth in the water rather than or instead of reducing it. So these are some limitations of activated carbon. What are the factors affecting adsorption equilibria? First, factors related to adsorbent, and second, factors related to adsorbate. So the adsorbent, the characteristics, the surface area, the pore size, the surface chemistry, all of this will affect the efficiency of adsorbent. And on the other hand, we have the adsorbate. The characteristics of the adsorbate, solubility, molecular structure and size, the degree of ionization, all of these characteristics will affect the efficiency of adsorbate. Alright, let's move to have some idea about the design formulation of the activated carbon. We have two main relationship, or we have two main isotherms that we normally depend or rely on when we design the activated carbon filters. Okay, we have the Freundlich and we have the Langmuir. So let's have a look. The Freundlich isotherm is expressed as x over m equals k c to the power 1 over n. So x is the weight of the substance that's going to be adsorbed, and m is the weight of the adsorbent. So x is the adsorbate and m is the adsorbent. C is a concentration of substance remaining in solution. Okay, so it is concentration of effluent. K and m, they are constants. They depend on different things like temperature, the adsorbent, the substance to be adsorbed, different things. So these are factors. Okay, now Freundlich isotherm or Langmuir isotherm, what is the governing or the control approach that we have to investigate both? We have to investigate which one fits more with the material or with the case that we are dealing with. Okay, so we can transform this form into we can transform the Freundlich equation into a linear equation, y equals mx plus c. So it will be ln x over m equals 1 over n ln c plus ln k, and this will be in the form of y equal mx plus c. So we can draw this we can plot. I mean, we can have a plotted graph, and we see if it is fitting well with our case or not. Now we will see some example to know how we use it. Okay, and the value of k and 1 over n has to be, or they have to be determined based on laboratory evaluation. So we make a lab experiment, then we can come out with the constants of k and n. Okay, so we have two approaches of lab experiments. Either we fix the carbon dosage and we apply a fixed carbon dosage on different time intervals, or we apply different carbon dosage with fixed time duration. Okay, now the second isotherm is the Langmuir equation. It is similar to the Freundlich, however the constants are somehow different, but at the end we can have also a linear equation of Langmuir. So we have 1 over xm equals 1 over ab times 1 over c plus 1 over a. What is a and what is b? A and b, they are constants. Okay, the a increases with increasing the molecular size. A is a constant related to the molecular size of the adsorbate, and b is the amount of adsorbed to form a complete monolayer on the surface. Okay, so basically b is related to the monolayer adsorption. And the equation, of course, can be written as linear equation, as we said just now. Okay, here's one example on Freundlich isotherm. Okay, this is a lab or data from a lab experiment. We apply different volumes or different masses of GAC on one solution. Okay, and each of them was applied for the same period of time. And then we got the equilibrium concentration, C equilibrium of the adsorbate in solution. Okay, so that means, for example, when we apply 0.001 gram of the GAC, okay, when we reached the 3.27, after that we couldn't reduce the concentration more. So the initial concentration is 3.37. This is the initial concentration. When we apply 0.001 of GAC, we could reduce the initial concentration up to only 3.27. So from 3.37 to 3.27. So that's what we call the equilibrium concentration. While when we apply 0.5, we could reduce it to 1.33. So this is the equilibrium equation. The question asks you to determine the Freundlich isotherm coefficient for the following GAC adsorption test data. Okay, the liquid volume used in the batch adsorption test was 1 liter. Alright, so we have to derive the values needed to plot the isotherm using the batch data. The C node, of course, the C initial is 3.37 for each dosage, and the C equilibrium was given for each dosage, as you can see. Okay, now X is the difference between C initial minus C equilibrium. Okay, C node minus C equilibrium, it will give you the value of X, which is the adsorbed material, and M is the applied adsorbent, So at the end we can have the value of X over M. Okay, so these are the values of X over M for each point. Now we can plot a graph between CE and X over M, and we take log for each axis to make it a log plot. Okay, so at the end we have the line, we have the trend line, and we can have the equation of the trend line with a very good R square value. Okay, so 1 over n is the slope, which is 3.558 here, and X over M, of course, will equal 1.55 times CE to the power 3.55. So this is the Freundlich equation that we derive from this graph. Okay, so log KF equals 0.1908. This is log K, okay, log of K from the equation here. So the K itself equals 1.55. So we just put it here as 1.55, and this is 1 over n, the slope. So we have the equation X over M equals 1.55 times CE to the power 3.55. Now we can, if we apply any value of X over M, we can know the exact value of CE. So that's that equation can be transferred from the lab to the site, from the lab to the real application or large scale application. Okay, next we have a example on Langmuir equation. Okay, we have a wastewater sample contains 25 milligram per liter of phenol. This is to be treated using the PAC, powder activated carbon, in order to produce an effluent concentration of 0.1 milligram per liter. So this is the targeted concentration. This is the initial concentration. Okay, the PAC is simply added to the stream, and the mixture subsequently settled in the following sedimentation tank. Okay, so the constants of Langmuir equation are determined by running a jar test, producing the results shown in the table that we will show just now. We will show after that, The volume of waste subject to each test is 1 liter. If the flow rate Q node is 0.11 meter cubic per second, this is the flow. Okay, so we have to calculate the quantity of PAC needed for the operation. So how much PAC we should apply to maintain this final concentration of phenol. Okay, and we have a flow rate of 0.11 meter cubic per second. Okay, and what is the adsorption capacity of the PAC? Okay, we have to calculate the quantity of PAC needed to treat the influent phenol to the ultimate residual concentration, which means to the least possible residual concentration. Okay, let's have a look on the data obtained. These are the test runs. We have a PAC added 0.25, 0.32, 0.5. We keep increasing the dosage until we reach 2.6 gram. And here the equivalent concentration of phenol, CE. The equivalent concentration reduced from 6, then 1, then 0.25, 0.09, 0.06, and we apply more PAC, but the equivalent concentration remained the same, 0.06, 0.06. Okay, although we add more, the concentration remained the same, 0.06, which means that we reach the ultimate possible residual. We reach the least possible residual concentration of phenol. So when we plot the data that we obtain, we have 1 over xm. Of course, we will apply the same as we did in the first example. So we will have the values of xm, and we have the values of CE for each. Okay, so we will plot the graph between 1 over CE on the x-axis and 1 over xm on the y-axis. So this is a main difference between Freundlich and Langmuir equation. And of course we have to draw a trend line. You can do it by Excel or you can do it on a graph paper. It doesn't matter. Okay, you have then you can get the equation y equals mx plus c. Okay, so the value of m is 2.86, the value of c is 10.522. The r square is very good. Okay, so the slope is 2.86, the intercept is 10.522. So 1 over a, this is the intercept. Okay, 1 over a, if you look at the Langmuir equation, 1 over a is the intercept, represented by c. Okay, represented by c in the equation, I mean. So a equals 0.095. 1 over ab is the slope in the equation, in Langmuir equation. So it equals 2.86, which means that b itself equals 3.67. So now we have the value of a and the value of b. Okay, finally we can write the Langmuir equation. 1 over xm equals this is the 2.86, 46 times 1 over c plus 10.522. Okay, so now we got the constants. Now at the concentration of 0.1, this is the targeted concentration. Okay, if you apply c equals 0.1, x over m equals how much? It equals 0.0255. Okay, substitute c as 0.1, you can get x over m as 0.0255. This means that 0.0255 kilogram of phenol to be removed using 1 kilogram of carbon for each 1 kilogram of activated carbon. Okay, so we need 1 kilogram of activated carbon to remove this amount of phenol. This amount of phenol. Okay, so the total phenol to be removed, okay, equals 0.11 times 25 minus 0.1. So this is the difference between the initial and the final. Okay, the total amount, because we are going to determine the amount of phenol removed, the phenol removed, and this is the flow rate. Okay, so 0.11 times 25 minus 0.1, okay, divided by 1000 to convert the values. So every second we are removing 0.00274 of kilogram of phenol. So this is the flow, or I mean this is the removal rate. This is the removal rate of phenol. So the PAC required for each day, okay, we can calculate for each day how much we need of PAC, because 1 kilogram, because 0.00274 kilogram per second of phenol is required, and we know for each we know that 1 kilogram of carbon can remove this amount of phenol. So that means we can know how many or how much the amount of PAC required per day to process the removal or the treatment process. Now the lowest concentration of phenol is 0.06 milligram per liter, as we saw we noticed. Now the lowest concentration of phenol is 0.06 milligram per liter, as we noticed from the lab data in the question. So at C equals 0.06, how much the X over M? X over M would be 0.0172 kilogram phenol for each kilogram of carbon. The total phenol to be removed, we can follow the same steps to know the amount of total phenol to be removed to the ultimate residual concentration, not only to the target. So we change this value to the ultimate. Okay, so for the flow rate, 0.11 times 25 minus 0.06 over 1000 equals this value, kilogram per second of phenol. Okay, so the PAC required, we follow the same steps before. We can calculate how much PAC required per day to remove the phenol to the ultimate possible value. Thanks for watching, and see you in the next videos. Assalamu alaikum wa rahmatullahi wa barakatuh.